Okay, in this PowerPoint, we're going to go over the renewable energy sources. That includes solar energy, wind energy, wave energy, and the other one, hydroelectric. Okay, as a quick review, don't forget that power is equal to work over time, or in other words, work is how much your energy changes, so change in energy per unit time. We're going to use that a lot in this PowerPoint. Hydroelectric is involving dams, and what you do is you store up a bunch of water behind a dam and you let it through, and that water comes through, spins a turbine, which spins a generator, which produces electricity. So what are the energy transformations? You have water stored up high, right? And so this is gravitational energy, and as it comes down, it gains kinetic energy, which spins the turbine, which is kinetic energy in the turbine, which spins the generator, which creates electrical energy. So here are the energy transformations. You should be able to draw a Sankey diagram showing these energy transformations. So again, we start with gravitational potential energy of the water. As it falls, it turns into kinetic energy of the water. That kinetic energy of the water spins the turbine, right? So some of the energy goes into the turbine, but not all of it does, because some of the water is still moving, right? It still has to go through. So it spins the turbine, some of the energy goes in the turbine, that energy then turns into electrical energy. So there is degraded energy because the water is still moving afterwards, not all of that kinetic energy goes into the turbine. Okay, there's another way you can get hydroelectric energy, and that's with a thing called tidal storage. So what they do is they put up, like where there's a bay or something, and if there's a narrow opening, they'll put up a dam at that narrow opening. And then they open this valve. So over here maybe is the bay, and over here is the ocean. So as the tide comes in, they open a valve and they let all that water get really, really high. And so during high tide, then they close the valve, and then they wait for low tide to go down, okay? And then once it's low tide on this side, the water is still high over here, so then they can open up the gate and they can let it through, and that change in gravitational energy, they can get energy out. And they can do that several times. Even if they have a turbine that goes both ways, they can actually get energy out going this way if they let water through, and then on the other side when they let water go through again. So they can actually get water or energy out several times. It's just not very consistent because it only happens several times a day. Okay, the advantages and disadvantages of hydroelectric energy are as follows. For the main pro is that it's pretty much free. Once you get it built, it is pretty relatively cheap to maintain, and so it just keeps on producing energy. Also, it's inexhaustible. Water's always coming down on mountains. It's also clean, meaning it doesn't produce CO2 or other elements that pollute the air, or even other tailing elements like in other waste elements like in nuclear power plants. Some cons are that it's very dependable on locations. You can't do this everywhere. You can only do it in certain locations. For example, Washington State is a very good place to do it because we have lots of mountains for water to come down, and we also have a lot of rain. So it's an excellent location for hydroelectric. However, other locations aren't as good. It also requires drastic changes to the environment. So whenever you build a dam, you're basically taking something that wasn't a lake and you're turning it into a lake. So if you've ever driven out I-90, there's a dam up there over near the pass, crossing over the mountains. And during the summertime, you'll see a lot of dead cut down trees, and in the winter, you'll see a giant lake there. So because you can't see the cut down trees, the stumps, there used to be a giant forest there. So during the winter, it's nice and high. And then in the summer, when they let that water run, you can see what it used to be. It actually used to be a forest there. Other things is that the initial cost is very high. It can keep on producing afterwards, but the initial cost is high. Another thing you need to know about is a thing called pump storage. Hydroelectric energy can keep on producing energy as you get a giant lake, and as you build a dam and get a giant lake, and all that energy comes down through the dam, and you can store and you can use all that energy, and it's constantly coming down. The problem is that sometimes you need energy and sometimes you don't. For example, at night when everybody's in bed, people aren't using as much energy, right? Or there might be certain times of the year where people aren't using as much energy. For example, the summertime, people don't use as much energy as they do during the winter, right? Just to heat their homes as well. So sometimes if you have an excess of water coming down, but you don't want to waste that water and all that energy that's coming from it, you can actually store the energy. So any excess energy you have, you can use to, instead of having water come down and lose gravitational, turning it into electric, you can actually do the reverse thing where you take a pump and you pump it up. So you pump it up into a lake, a high lake into a high mountain, okay, and you store that water kind of like a battery. And you're storing that energy instead of in electrical batteries, you're storing it in basically like a gravitational battery. So then later on, maybe you pump it up during the summer months when energy is not needed very much, and then during the winter months when everybody starts turning on the heaters again, you can then let that energy back down, or the water back down, and then turn that stuff back into electrical energy. And that way you're storing energy when you have low peak times or low peak requirements for energy, and then you can pull it back down when you have a lot more requirements for energy. This is called pump storage. Is there an equation in your yellow packet for hydroelectric dam? Let's take a look. On your topic 8, okay, I don't see any, at least, let's see here. Where is that energy coming from? It's coming from gravitational. And I don't see any equations that have anything with gravitational energy. So the answer is no. There is no equation for, at least not in your packet, for hydroelectric dams. So how are you going to get that equation when you need to solve things for hydroelectric dam? You just think about, where is this energy coming from? It's coming from gravitational energy, right? So we know, again, power is equal to your change in energy per unit time, right? So we're going to calculate power output by simply taking the change of energy, which is our gravitational energy. So our change in energy, which is gravitational, mgh, and divide it by time. This is the equation you're going to use to calculate the power produced by a hydroelectric dam. And it's easy to remember as long as you know where that energy is coming. Let's do a practice problem with hydroelectric power. Here it is. What is the power output of a 70% efficient dam that has water starting 200 meters high and has a flow rate of about 500 liters per second? Now, if you remember right, efficiency is the amount of power you get out divided by the amount of power you put in. So if we knew how much power we put in and we know the efficiency, so if we know the power in and we know the efficiency, we can solve for how much energy we get out of this. So how is this energy going into our system? It's starting up high as gravitational, coming down and then going through the turbine and then coming out as electrical, right? So the power in is going to be your original gravitational potential energy. So we need to calculate that power going in from gravitational energy. So rearranging this, we just plug in 0.7. We just need to get the power in, then we can find the power out. So we know that power in is going to be gravitational energy per unit time. But in order to solve for that, we need to get gravitational energy. So we know gravitational energy is mgh, right? So let's see here. H, it starts 200 meters high, right? We also know that G is 9.81, of course. The mass, though, one of the main things you need to know with hydroelectric is you need to remember that because you're usually dealing with water, 1 liter of water is equal to 1 kilogram of mass, or has 1 kilogram of mass. So if there's 500 liters of water every second, that means that there's 500 kilograms of mass going through every single second. So let's just worry about 1 second at a time. We'll say the mass that goes through then is 500, right, because it's after 1 second. We'll plug all these numbers in. We'll get the energy to be this large number here, 981,000 joules, and that's how much energy is going out every second, right? So we'll take that, we'll plug that EG into here. The time is, again, 1 second, because we use the mass in 1 second, right, liters per second. And so we calculate the power to be the exact same number. Now we're going to get the power, take this number, and we're going to plug it into the stuff that goes in. This gravitational energy is going into the machine, right? And then out is coming electrical energy. So how much electrical energy is coming out, or what's the power output? And we take this number, multiply it by 0.7, and we get a total of 686,700 joules. And this is the power output. Oh, sorry, that's supposed to say watts. 686,700 watts of energy. This is the power output.